Okay, so in this video we're going to talk about the EPR spectroscopy. So this technique is used when metal ion complexes have to be identified, right? We can use this technique to identify metal ion complexes. What we need here is unpaired electrons. What are unpaired electrons? Let's take example. If A is a metal, we can write the electron configuration like this. So here we have put electrons. These are paired electrons, right? These are paired electrons, and this is unpaired electron. Every electron contains two states, which is one is 1/2 and the other one is -1/2. These two states are based on its rotation and magnetic field, right? So the electron can either be on this state or this state, or they can easily flip into one another. Now what we are trying to do here is we are going to apply a magnetic field, right? We are going to apply a magnetic field. Here we have our electron, so it has two states. One is 1/2 and one is -1/2. Now we have applied the magnetic field. So what happens over here is, these two are based on magnetic fields, right? Either two directions. So it will align with our applied magnetic field and split into two energy levels. So this is basically 1/2 and -1/2. Our magnetic field, our applied magnetic field, will create an energy gap delta E, which can be calculated by this equation G mu B B naught. This B naught is the applied magnetic field, and G, this is called Land's G factor, and this is another thing which is called Bohr magnetism. Right, so by this equation we can calculate this specific energy gap. You can identify that by increasing our applied magnetic field we can increase this energy gap, right? We can increase this energy gap. Now what we're trying to do here is, after applying this magnetic field, we know now the two states have been split by some energy gap. This is the most stable one, so most of our electrons in the samples will be in this state. Now we are going to send in some radiation contains some specific wavelength, right? And check whether this electrons, whether it absorbs this radiation or not, because the energy is quantized, right? Energy is quantized, so it will absorb only a specific energy. So every wavelength which we are supplying over here won't be absorbed by these electrons. It will absorb only the specific energy which relate to delta E. So we have input some radiation, it contains some wavelength, and we are going to adjust this wavelength, right, until we give the sample gives some peak whether it has absorbed, right? We are going to identify the specific wavelength which the sample is going to absorb, which is related to this delta E. That's what we are going to do. So our graph will be coming like this. With the time we will have some absorption peak like this. This is absorption peak, but for the calculations we are going to take the first derivative of this peak, which is like this one. This is the first derivative, right? Why we are taking the first derivative is this contains more details, right? This contains more details. We will talk about the next videos. So what you need to understand is the technique. So this is the technique what we are using here by EPR spectroscopy.